Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we'll see how electrons behave in actual solids. Just to review what we have discussed so far. So in the beginning I told you that the most important part of a device is of a field effect transistor is its channel, and the channel can be sort of understood as a two terminal device where we have a channel, there is a source and there is a drain. And on application of a positive voltage on drain terminal, electrons flow from source to drain. Now as we know that in modern devices this channel region is getting smaller and smaller, and now this channel region is nanometer in length, and that is basically causing, as we know, and this we have already discussed, this is causing a fundamental change in the way electrons behave in the devices. And that is what we are trying to understand in this course. That is what we will be trying to understand in this course, and that is what we have already, that discussion we have already started. So ultimately in devices everything is basically the game of electrons, everything is basically the dynamics of electrons, how electrons behave in devices. That is what we essentially need to understand in order to understand the physics of the device. And in nanoscale, nanoscopic devices, when the channel region is few nanometers in length, electrons nature is no longer of a classical particle. Electron behave as a quantum particle, and that is why we started our discussion with the basics of quantum mechanics. We discussed the basic postulates of the quantum mechanics, and as you might recall, some of the postulates of quantum mechanics are fundamentally different from the classical mechanics. So for example, in quantum mechanics we have a wave function to describe everything about a particle or a system, and we on doing measurement on a quantum system, there is no deterministic result. We get one of many possibilities as the outcome of the measurement. So quantum mechanics is fundamentally probabilistic, whereas the classical mechanics is a deterministic science. We have also seen other postulates, how we define operators which correspond to physical observables in the system, and after going through the basic postulates of quantum mechanics, now after going through the basic postulates of quantum mechanics, we went on to understand the free electron, how a free electron behaves. So this is the first step in order to understand how the electron behaves in a solid. So we started with how an electron behaves when it is entirely free. It is free from all the interactions, all other particles, as if it is alone in the universe. In case of free electron, we saw that the Schrodinger equation of the electron looks like a simple second order differential equation, where we have a parameter called k, which is also the known as the wave number. Just to sort of remind you, a wave number can be understood as frequency in spatial dimension. So it basically tells how a wave or how a wave function is distributed in the space, how it is oscillating, how it is essentially repeating itself in the space. So, it is also known as the frequency in special dimension, and we saw that for a free particle case, for a free electron, when the electron is free from all the interactions, the electron wave function looks like a sinusoidal, just a plane wave where the wave function is a superposition of sine and cosine. And in this case, the relationship between the energy of the electron and the wave number of the electron is a parabolic relationship. So, for a free particle, if we plot Ek relationship, it is a parabola around E axis basically. So, that is what we saw. This is a simple solution, a simple case of quantum mechanics which we can handle analytically. Generally, it happens that in quantum mechanics we cannot solve Schrodinger equation analytically precisely solve. So, we need to make many approximations, but for free electrons we can solve the Schrodinger equation analytically, and this is how the solution looks like, and this is the Ek relationship for free electron. Okay. After free electron case, we tried to understand how the electron would behave when the electron is confined in a potential well. What do we mean by a potential well? Potential well has potential has sort of potential boundaries between those boundaries the potential is 0, and in those boundaries, beyond those boundaries, the potential is infinite. So, what it means is that the electron is now confined between 2 points or 2 boundaries by a potential. And in this case, we saw that now the electronic wave function is still a sinusoidal wave function, sinusoidal kind of wave function, but the energy values are no longer a continuous set of values. Now, the energy values are discrete values which are given as n square pi squared h bar square divided by 2 m a squared, which means that in a potential well electrons can take only a certain set of energy values. It cannot have any arbitrary energy and exist in the potential well. It can only take certain set of energy values, and corresponding to those energy values the electronic wave function will be defined by this equation. And these are some of the simple wave functions corresponding to various energy values. And in this case we saw that now if we plot the Ek relationship for a particle in a box, it will not be a continuous plot because the energy values do not exist for all k values. The k can only take, the wave number can only take n pi by a, these values where n is an integer. So, the Ek plot will be a discrete plot where the E values will still be lying on the parabola, but it will not be a continuous plot, it will just be the points on this parabola like this. So, only these points will constitute the Ek plot for a particle in a box. So, we consider two cases, one is the electron when the electron is entirely free, and second case when the electron is entirely confined in a potential well. And there are a range of intermediate cases, there are lot of cases in between. For example, we can have a finite potential well where this potential V is not infinite inside on the boundaries, it is a finite value. So, V is no longer infinite, and in those cases also we can solve the Schrodinger wave equation and we can find out the electronic wave function, which will basically be like a hybrid of free electron and the electron in an infinite potential well. Now, the key takeaway from this understanding was that when the electron is confined, it leads to discretization, and this was one of the earliest feature of quantum mechanics which was discovered, and it was a paradigm shift in understanding of particles and their natures. Okay. So, with this understanding, now we will see how electrons behave in solids basically. So, as you know, as all of us know actually, that solids can be quite complicated. They are not like free particle case, or not even like particle in a box case. They can be quite complicated. Generally, the solids in devices that we use in devices are crystalline solids. They have a regular defined lattice structure, and but still at finite temperatures, those lattice points, the solids and the lattice points might be vibrating, and the solids might have many sort of non-idealities. For example, there might be a lattice vacancy, the lattice points are all vibrating. So, these kind of complications might be there in solids. So, we will not directly go into an actual solid actually, because it is not possible to solve Schrodinger equation analytically for an actual solid, for an actual lattice. So, what we do is we take the case of 1D solids, first 1D solids, and this case can easily be generalized to our 3D solids. And moreover, in 1D solids we do not consider lattice vacancies and lattice vibrations. So, we do not consider these two known idealities, and we first consider an ideal 1D solid. So, an ideal 1D solid will look something like this. So, in a 1D solid, the atoms, or to be more precise, the atomic cores will be located at a regular interval from each other. So, let us consider the case of an infinite 1D solid in which these atomic cores, basically atomic cores are atomic nucleus plus tightly bound electrons. So, atomic cores are atomic nucleus plus tightly bound electrons. So, the atomic cores, and generally they have a positive Z Q Z E charge. So, what it means is that in an atomic core, a nucleus is there, and some electrons are so tightly bound that we consider this entire system, this atoms plus tightly bound electrons, as one system, but Z number of electrons are free, which means that from each atom Z number of electrons are free to move in the entire solid. So, that is why the atomic cores have a positive Z times E charge, where E is the charge of a single electron. So, these atomic cores are positively charged stable atomic or stable heavy atomic cores basically. So, these are fixed at a regular interval. The period of this lattice is, let us say, is A. Now, if an electron exists in this system where there is a chain of atomic cores, and we bring sort of one electron here. So, now we will try to see how an electron will behave in this particular system. And as we can see that in this system also, like particle in a box system, the potential is no longer 0. There will be some potential that the electron will feel because of the atomic cores. But just take a moment and think what will be the potential energy of the electron in this particular environment. So, in this environment, as you might recall, the potential due to each atomic core will be a constant times the charge of the atomic core k times q, q is the charge of the atomic core, which is basically z times E in this case divided by r, and the potential energy of the electron would be the charge of the electron, which is minus E times E into k q by r. So, the potential energy of the electron in presence of a single atomic core will be basically something like k times if we put the value of q to be z e square divided by r. So, it is inversely proportional to the distance between the electron and the atomic core. And if we plot this on corresponding to each atomic core, we will see how the potential profile looks like. So, corresponding to each atomic core, the potential would be this, basically inversely proportional to the distance between the electron and the atomic core. So, now let's see how it actually looks like. Potential due to atomic core, due to let us say this atomic core is this. As we can see, this is basically the potential energy of the electron is inversely proportional to minus 1 by r. So, the potential energy of the electron will be this. This is a graphical representation of the potential energy. This is we are not in order to sort of have a good understanding of the nature of electrons, we will sometimes use graphical representation of the systems and their various parameters. So, the potential energy of an electron when it comes close to this atomic core will be this, and similarly this will be the potential energy of the electron whenever it comes close to any of these, basically any of these atomic cores. So, we can individually say that corresponding to each atomic core in the lattice, the potential energy of the electron will look like this. So, the resultant potential energy of the system would be basically a sum total of all these potential energies. So, that will be the final potential that the electron will see or electron will feel in this particular lattice. Let us see just for an exercise, let us see how this potential energy looks like. So, let us say if the potential energy due to this atomic core is this and potential energy due to this atomic core is similarly can be plotted to be this. So, the resultant potential energy of these two from these two atomic cores will be something like this. So, this is the resultant potential energy of the electron in presence of two cores, two atomic cores. Okay. And similarly, for a chain of atomic cores, the resultant potential energy of the system would be like this, but extended to all the atomic cores. Okay. So, if we generalize basically this understanding, this is how the potential profile, or to be more precise, the potential energy profile of the electrons would be in a 1D solid. So, in a 1D solid, if we precisely plot the lattice here, the potential energy of the electron in this system would look something like this. So, this is how the potential energy would look like. So, this is the potential energy of the electron in a 1D solid, and as you might recall, the so ultimately we need to solve the Schrodinger equation for electron in any system in order to understand the nature of electrons or the behavior of electrons in that system. And the Schrodinger equation looks like this. In 1D it would be minus h bar square divided by 2m del 2 by del x2 plus ux, where ux is the potential energy, times the wave function equals energy of the electron times the wave function. Okay. So, as you can see, this parameter ux is quite important in solving the Schrodinger equation. So, if we need to understand the behavior of electrons in 1D solid, we need to put, instead of in place of this ux, we need to put this potential profile in the Schrodinger equation, and we need to solve this Schrodinger equation, and finally the wave function that we will obtain will be the wave function of the electrons in this 1D solid. So, that will basically capture all the information about the electrons in this solid. So, that is what we will try to do, but there is a catch here. Schrodinger equation is not easy to solve always. Schrodinger equation generally is difficult. In most simple cases it can be solved, but as soon as there are multiple atoms, there is a complicated interaction between the atoms, it becomes difficult to solve the Schrodinger equation, and that is also the case here. With this potential profile, if we take precisely this potential profile for 1D solids, we cannot solve the Schrodinger equation precisely. But there is a way out here, and this was given by Kronig and Penny, and that is why it is known as the Kronig-Penny model. So, the technique that they use is that instead of solving the Schrodinger equation for this potential profile, they sort of approximate, or they solve the Schrodinger equation for a potential profile which is not exactly the same as the potential profile of 1D solids, but it resembles quite well with the potential profile of 1D solids, and this is the profile that the Kronig-Penny model takes. And instead of having negative infinite potential energies at certain points, which is the case at these points, the Kronig-Penny model takes a finite value of potential energy at these points. So, in this particular figure, it is taken to be as the reference point, and the potential energy is considered to be 0 at these points, and the upper value of the potential energy is taken to be u naught. So, this is not exactly the same profile as is there in 1D solids, but this resembles quite well with the profile that is there in the 1D solids, and it turns out that that this profile captures the most essential behavioral, most essential characteristics of electrons in solids. So, if we solve Schrodinger equation for this profile in solids, it will basically capture all the essential components, all the essential characteristics of the electrons. So, that is why we solve the Schrodinger equation for the potential profile taken in the Kronig-Penny model. And it also turns out that the Schrodinger equation can be precisely solved if we take ux to be this profile with some mathematical techniques. So, this is what we will do in order to understand the nature of electrons or the behavior of electrons in solids. We will solve Schrodinger equation for this potential profile, the potential profile given in the Kronig-Penny model. Okay. So, that is going to be our sort of next task. Again, as you might have realized, this is an infinite sequence of atoms. In a 1D solid, the atoms are can in principle be from minus infinity to plus infinity, but generally solids are finite in length, but the length can be extremely large on atomic scales. So, for all practical purposes, this can be taken to be quasi infinite in length, which means a huge number of atoms are there in the solids, which means there are huge number of such patterns in the potential profile, as you can see here. If you closely observe in this potential profile, this particular pattern, this pattern starting from here to here, this is repeating itself for a large number of times for the entire length of the solid. So, if we need to solve the Schrodinger equation for this entire solid, essentially we would need to solve the Schrodinger equation for the entire length, because the potential is changing. It is as if there is a sequence of potential wells and or potential barriers in the solids, and that in itself is also an extremely difficult task. But there is a rescue here, I would say, and the rescue is given by the so called Bloch's theorem. So, what Bloch's theorem says is that if a potential is repeating itself, which means if there is a periodic potential, then the wave function follows a certain pattern. So, what Bloch's theorem says is that if a quantum system is in a periodic potential, which means let us take the period of the potential profile to be capital A, because we are taking small a here. So, even in the statement of the Bloch's theorem, let us take it to be capital A. Okay. So, if the potential is periodic, which means that after a period of capital A length, the potential is again the same, then the wave function will be of this kind. Psi x plus a would be psi x times exponential I k times a, the period where a is the period of the crystal. So, in simple words, or in simply it can be understood that if the potential is periodic, the wave function of the system will also be periodic, but modulated by an exponential. Okay. Or a restatement of the Bloch's theorem is that in a periodic potential, which means if the potential profile is like this, then the wave function of this system is exponential ikx ux, psi x is exponential ikx times ux, where ux is a periodic function. Okay. So, these two statements of the Bloch's theorem are equivalent, and we will see here. So, in this expression, if we put psi instead of x, if we take psi x plus a, it will basically be exponential I k x plus a times u x plus a. And as we know, u x plus a is essentially u x, because u x by definition is a periodic function. So, this psi x plus a would basically be psi x plus a would be exponential I k x. Let us also decompose the exponential ux. So, in place of ux plus a, we can put ux in this expression, and exponential ikx times ux is basically psi x, as is clear from this equation. So, psi x plus a would be exponential I k a times psi x, which is essentially the earlier statement of the Bloch's theorem, this statement of the Bloch's theorem. So, the Bloch's theorem can equivalently be put in two statements. In a periodic potential profile, the wave function of the system would be psi x plus a equals exponential I k a times psi x, or psi x plus a, psi x can be written as psi x equals exponential I k x times u x, where u x is a periodic potential, which means u x plus a is same as u x. Okay. So, these are two equivalent statements of Bloch's theorem. We will not be going into the derivation of the Bloch's theorem in this class, but I would highly recommend you to go through the derivation of the Bloch's theorem, which is available in many standard texts on solid state physics and condensed matter physics. This will be an interesting exercise. This will clear many quantum mechanical concepts as well. Building on Bloch's theorem, so I am taking a detour in order to go into the details of Bloch's theorem here. This also means, this statement of Bloch's theorem means that this statement psi x plus a exponential I k a times psi x. This means if we take the first derivative of Bloch's theorem, it would basically be del psi x plus a divided by del x equals exponential I k a times del psi by del x. So, these two statements of Bloch's theorem are equivalent to each other. So, in other words, the Bloch's theorem can be stated in terms of psi x plus a, which naturally implies that the same expression holds true for the derivative of the wave function as well. Okay. So, there are two statements of Bloch's theorem, this one and this one, and as we have seen, these two are equivalent statements, and the implication of this statement is that the derivative of the wave function can also be represented in the same form. So, today what we have seen is that the interior of solids or the potential profile in solids is slightly complicated, and we need to make some approximation in order to sort of solve the Schrodinger equation inside the solids, and that approximation was done in Kronig-Penney model of electrons in solids, and there also we cannot just take the potential profile and solve the Schrodinger equation. There also we need to invoke Bloch's theorem, and in next class, in next lecture, we will see how by using Bloch's theorem we can analytically solve Schrodinger equation in 1D solids with Kronig-Penney approximation. Thank you and see you in the next class.